Start recording. So the first thing you have to understand function transformations is you have to understand parent functions. And I've mentioned this briefly in here several times. Do y'all remember what I mentioned when I said parent functions?
Yes.
It's a basic function. It's, bless you. It's a function before any transformations are done on them, okay? And by transformations, and we're going to go through every single transformation of a function, but I'm talking translations, slides, left, right, up, down. I'm talking about shrinks and stretches. Shrinks horizontally, stretches horizontally, vertically. And I'm talking about reflections over X and over Y. Okay, so those are all the transformations we're going to talk about. But before we do any of that, so, for example, y'all have been graphing the absolute value, right? This should help you understand absolute value if you're struggling with it. Before any transformations or anything is done to it, my basic parent function for absolute value is just simply the absolute value of X. When you graph this, it looks like 0, 0, 1, 1, bless you, 2, 2, negative 1, 1, negative 2, 2. This is my basic parent graph of an absolute value, right? Do we all understand? Nothing's been done, it's just the function itself. Okay? Another one that you will be, and you'll mainly be working with quadratics and absolute values, maybe some lines here. What do you think the parent function for a line is? Y equals X. Okay, parent function, linear parent function. Linear would be Y equals X. And it just looks 0, 0. It's the same thing as that absolute value graph. The only difference is that negative portion is not flipped up, right? This is a linear parent function. It sure is. Okay. And we will learn tons of parent functions, but for right now, we'll stick to these three. We'll stick to absolute value, linear, and although you'll be able to tell me some transformations on other parent functions, and a quadratic. And this one you may not know as well, but that's okay. Y equals X squared. It's a parabola. That's exactly right. It's a parabola. I get confused because I teach pre-cal right before y'all come in, and we're knee-deep in quadratics right now, so. All right. 0, 0, and you can just plot some points here so you see 1 squared is 1, 2 squared is what? 4. Then if I go on the other side, it's kind of like if you think about absolute value, because whenever you square something, you're always positive, right? So if I square negative 1, I get positive 1. If I square negative 2, I get positive 4. So I end up with this nice parabola. Looks like this. Again, there's no transformations that have been done to it. This is the parent. Everybody okay on those 3 parent graphs? Basic functions, yeah. Like reflect over Y? I'll show you. It's going to be the same.
Can I just turn it upside down?
All right. So we're going to talk about really algebraic transformations, and then I'll show you what it looks like graphically, okay? All right, y'all ready, Freddies? Here's the good stuff. Remember, have we talked about function notation in here? I thought we had. We have. So, like, I can say, because it's a function, I can say f of x equals x squared. Okay. No? I'm pretty sure we have.
Keep going through it.
Just real quick. All right. So, f of x tells me, because it's written this way, it tells me first off that it's a function, right? What does it mean to be a function?
It passes the vertical line.
Passes the vertical line test. One and only one output for every input. Okay? Every x has one and only one y that pairs up to it, matches up to it. We read this as f of x, and it simply tells me that what I put in is here. That's my input. F of x is my output. It's the same thing as y. So any point on the line is x, y. I could also describe it as x, f of x. F of x is what I get back out of it. Okay? And you can put anything inside those parentheses there. This just is a more sophisticated way to write y equals, but it indicates that it's a function. Okay? And we're going to be using this extensively. We won't really use any more y equals type stuff. Y'all remember now?
Yeah, I thought you were talking about the x squared part.
Yeah. No, just the f of x. Just the f of x.
Sure wasn't anything more.
No, that's it. That's it. That's it. That's it. All right, so let's talk about translations first. What are translations? Slides. That's right, slides. When you move it, when you slide it. If I start out with f of x, okay? Come on. And to that, I add some value c. Okay? So to the whole function, not just to x, but to the whole thing. That tells me that it is a translation up. So this would move up c units. Okay? Because it's plus.
Does the colon mean translation?
No, the colon just means that's what you do when you see that.
F of x is just like the graph part.
Yep. So if I started out by defining f of x equals, we'll do that absolute value of x. That's my function. Okay. Then what this is saying is, if then I took this and I said, okay, graph the absolute value of x plus 2. That means you would take that exact same absolute value function that I had, right? So initially it looked like, remember it looked like this when we graphed it, that parent function? It would move up 2. 1, 2. Everything shifts up 2. Every single point shifts up 2. This whole graph moves up 2 units. It's just an upward shift, yeah.
So we have to graph the first one?
Yes, you would graph the parent and then you would translate from there.
So with a plus 7, I know it's like, oh, that's a 2, never mind. The glare is weird.
Oh, I'm sorry.
So would that be on like the side with the absolute value of x or on the side of f?
It'd be over there.
Okay.
Yeah, it'd be over there. That's certain, yeah.
If the plus 2 is an absolute value, would be the...
It's a horizontal shift instead of a vertical shift. We'll get there. We'll get there. All right. So along those same lines here, if I subtracted a value from the entire function, and remember, I'm using f of x to describe the entire function. So if I say f of x minus c, that means I'm writing what f of x is, absolute value of x, and then I'm subtracting c from it at the end. Okay, so I'm just tacking it on to the end of the function. What do you think this means? Translation down c units. Okay, so again, if I take that same function, f of x is the absolute value of x, then if I said f of x equals absolute value of x minus 1, that says take the parent graph, take the green graph, and slide the whole thing down 1. Just 1. And so that's what that would look like. Does that make sense? Mm-hmm. And right now I'm not getting very precise and exact. Right now I want you to understand what the shifts are doing. Okay? So adding it to the end of the equation is taking it up, and subtracting it from the end of the equation is taking it down. That's what we're fixing to do. Absolutely. Yep. Okay. Everybody good with these are vertical translations. Mm-hmm. It's to the whole function. And I could do this to absolutely any function that I have in the whole wide world. If I took, if I had f of x equals x squared, and I know you don't know how to graph this, but I'm just saying, if I had this one, and I said g of x equals x squared plus 3x minus 5, what's the difference in f and g? Well, it's what? Minus 5, which means I take this and move it down 5. It's just, that's what it is. It's a vertical shift. I'm fixing to show you that. All right, everybody okay on vertical shifts? All right, let's do horizontal shifts because y'all are just antsy to get there. Horizontal translations. Bless you. But it's backwards. If I have f of x plus c, this tells me that I move left c units. It's the opposite of what you think. That's why it gets a little tricky, a little sticky. Okay? So plus c means left. Minus c is right. If you plugged in the points, it would make sense. Okay? So if I take my same f of x, we're going to run absolute value in the ground here. If I define f of x as the absolute value of x, okay, what this would look like, what is, let's say I had f of x minus 2. That's going to look like this, not a parenthesis. Right? So it's going to take that same initial, and I'll do my initial in green again, my parent graph. And it's going to take it, instead of shifting up and down, it's going to move right to the right, to the right. Y'all are kind of dead this morning. So that's what my translated graph looks like. Yes. It's the opposite in there. Yeah. Well, you do, but whenever you plug it back in and then you evaluate for y, like think about this. All right, let's do this. If I plugged in 2, what do you get for y? If you plug in 3, what do you get for y? If you plug in 1, what do you get for y? Absolute value.
So why can't you do that for plus?
Well, if you do plus, now remember plus is going to move which way? Left. So let's say I did f of x plus 2. This is going to be a shift left. Or it should be. Let's plug it in and see. What do you get? Remember, I want to do 0 and then 2 up, 2 down, right? So it's 0 at -2, or it should be. Plug it in, you get what? 0. What about -1 and -3? Right? So it's shifting it that way. It's the opposite of what you'd think it's doing. So when you add to x, you're shifting left. When you subtract from x, you're shifting right. Does that make sense so far? You would think it would be the other way. Tell me what this is doing. If my parent graph is x squared, it's a parabola. My parent graph is x squared. How is this compare to the graph f of x equals x squared? What's the difference in these two? What's happening?
You're shifting left
Left how many?
2 and then moving down.
Left and down.
Left and down. Okay, so my parent graph 0, 0, 1, 1, negative 1, 1. So my transformed graph is going to be left 2, 1, 2, and down 1. If it's hooked to the x, it's left to right. If it's outside everything, just tacked on the end, it's up and down. This one, again, left 1, 2, and down 1. Left 1, 2, and down 1. There's my transformed graph, my slid graph. It just slid left and down. Choop, choop. Does that make sense? Transformations are the easiest. Translations are the easiest of the transformations. We're doing translations, reflections, and dilations. This is translations. But yes, it will be about like this. Compare it to the parent graph. What is it doing?
Okay, that sounds so nice. We're not supposed to know how to graph.
You can graph the parent one, the 0, 0, 1, 1, negative 1, 1. But as far as, and then transform from there. All right. All right, I should have put a 1 by translations, but okay. 2 is reflections. Do what? Yeah. All right. F of x, yeah, everything, this is all 2/6 today. F of x is my parent, whatever I decide to define as my parent graph, okay? 2 types of reflections that we're going to talk about right now, okay? The first one is if I negate everything in f of x, okay? So you got to think about this. If I put a negative in front of f of x, that kind of means whatever f of x is, I'm going to put a negative out in front of everything. So it would apply to everything inside there, okay? And I don't want to leave this here because it's not really my parent graph, okay? When I do that, so really I'm negating y, okay? Because by negating y, I'm negating everything in the equation. This is a reflection over the x-axis. Okay? So if I change the sign of everything in my equation, it's flipping over the x-axis. Remember reflections from geometry? So guess what you think happens if I only negate the x's over the y-axis? So it's the opposite again of what you think. Okay, if you negate y, you reflect over x. If you negate x, you reflect over y. No, are you stressing out on me over there? I can see it in your eyes. It's okay. When we pull it all together, it's going to be okay, I promise. Okay? All right. So, again, let's use our same absolute value of x. If f of x is the absolute value of x, and you can do this algebraically, you can plug them in and look, and you can see what's happening. let's say I asked you to find or to graph negative f of x, okay? So this time it's reflecting over what? X-axis, right? I'm just going to flip it over the x-axis. That's all I'm going to do. 0, 0 still? 0, 0, right? Reflecting over x-axis negates what? Whenever you think back geometry, y'all should have reflected shapes in geometry, right? So if you had a point that you wanted to reflect over x, then you negated what? The y, right? You remember doing that?
Yes.
You should remember to, like if I was asked to reflect this square over, I would take all the points I needed to graph the square and just negate all the y's, and it would automatically flip it over x. I know y'all did projects like that in Miss Wilson's class because I saw y'all doing them. Yeah, okay. So she didn't teach you algebraically? Okay. So, okay, anytime you reflect over x, you negate y, which makes sense with this, okay? So 1, 1 becomes 1, negative 1. And negative 1, 1 becomes negative 1, negative 1. To reflect over y, you keep x, to reflect over x, you keep x, but change y. Does that make sense? And you can see it graphically, okay, but algebraically, when we reflect, that's what we do. Yeah. Parent. We're always working from the parent graph, which is just absolute value of x, yeah. So then, in that same thinking, if I negate x, then I'm reflecting over what? Over y, but look at my graph. 0, 0 stays the same. If I have the point 1, 1, and I negate x, it becomes negative 1, 1, and this was negative 1, 1. If I negate that, it's the same graph.
So by negating it, you're just
Multiply by negative 1.
Okay.
Opposite sign.
Wait, so the green is right?
The green is a reflection over x. The purple is a reflection over y. As long as it's symmetrical about the y-axis, then a reflection over y is going to be the same graph.
So you put one graph.
Yeah.
How would you do a reflection over y-axis? Wouldn't it like not be a function?
Well, it is, but everything kind of flips places. Like the left side becomes the right side and the right side. But if it was symmetrical to start with, then it's the same graph.
Then it has to be symmetrical to start with.
This one does. This one does. Yes, it'd still be, because a reflection over y. Now, if I had something that I was, say it wasn't at the origin, okay? Let's say, and you're really getting into further down the road. But if I took a function that had already been translated and tried to reflect it, then I'm going to start. But yes, you could reflect it over x and you could reflect it over y. You could do both.
Are we ever going to reflect it
Yes.
over
Over the line, y equals
the
x.
diagonal?
At some point you may, yes. That's just negating both. We'll get, don't worry about it. All right. Everybody okay on reflections? Because I've saved the, yeah. Yeah. All right, get through it as best we can. All right, so dilations. And yes, Noah, you are correct. Dilations is a word that you should have heard in geometry. In fact, all of these transformations you should be very familiar with from geometry, which is why geometry is a handy thing to have before Algebra 2, right? All right. So, and before we did it this way, it was, you'd have to wait to do this, you know what I'm saying? Because you wouldn't understand all the geometrical terms. All right, so dilations. Dilations are what I like to call shrinks and stretches. Your book does not use the word shrink, it uses the word compression. Of course it does. So just understand that those two are the same. Stretches, they call it stretches. Yeah. Compressions and stretches. All right. There are all types of dilations, though. Okay. So you can get bigger or you can get smaller. And these really, we're going to have to take some points to plug in to understand what it is it's doing. But I want you to be able to identify if it's shrinking or stretching and which way it's shrinking or stretching. All right, so here we go. If I have my same parent function and I multiply by some number, and you're going to see that some of these can be both vertical and horizontal depending on how you look at it. Okay, I think that's why it gets a little confusing. If I multiply by some number on the outside of f of x, okay, some number a. Now, as I do this, I'm going to have to think about the absolute value of a, because the negative, if it's negative, that's going to deal with a reflection, right? We say if there's a negative out front, it's reflected over x. So I don't want to look at the negative. I really want to look at the absolute value of a as I analyze this, okay? If a, or the absolute value of a, is bigger than 1, it is a vertical stretch. Isn't what always?
Like absolute value.
Yeah.
Less than 0.
Well, but you could have, if you had -3 in front,
Oh, like
That's-
besides 1?
the negative is going to deal with reflection. The 3 is going to deal with dilation.
So like if you have 1 as A and then -3, that would be -3 is not greater than 1, so there would be some.
Well, the other one's going to be the absolute value of a is less than 1. Yeah. So you're talking, if you're talking about absolute value of a less than 1, and you're only talking about positive numbers, what are you talking about, really? Say again. Decimals and fractions. Okay? So you're really looking between 0 and 1. Okay? Because if you're taking absolute value, it's not going to be negative, right? All right. So if you're multiplying, and vertical, because y is vertical, I'm multiplying everything by y. So then this is a vertical shrink. Now think about what this means. Literally, I wish one day I'm going to have a nice visual for this. If I'm talking about a vertical stretch, okay, if I have this nice little parent graph like this, if those ends were rubber bands, if those axes were rubber bands, and I could stretch vertically, what's happening to my graph as I stretch out vertically? Thinner, right? Think about it. If you were here, okay, and you pulled on the ends. So a vertical stretch is shrinking it in, right? Does that make sense? You sure? I feel like no.
So the shrink would make it fatter. That reminds me of
If I stretch vertically, okay, if I started shooting up, I'm going to get skinnier, right?
Yes.
I know, right? Somebody stretch me. Just grab hold and just stretch me. But
Morticia, when she stretches.
Great. Okay, so a vertical stretch on this would look like this. Vertical stretch. Okay, even though it's saying stretch and you're thinking stretch means bigger, you got to look, I'm talking about a vertical stretch, which means I'm stretching out, okay? Now, in the same thing, if I'm talking about a vertical shrink, so if I took this graph and I shrunk it in this way, you smush in the ends vertically, it doesn't have any choice but to go out, right? So a vertical shrink is going to do that to the graph. Yeah. That's where you'll have to put points in to see. Okay? Now, of course, we're not only talking about vertically, we are also talking about. So we could talk about f of a times x. Now I'm talking about horizontal dilations. Okay? We are really just skimming the surface here with transformations. We will delve so much deeper into this as we go. But this is really just getting your feet wet with these, okay? All right, so here, if the absolute value of A is less than 1, y'all ready? It's a horizontal stretch. Most everything horizontally is opposite. Okay. This you're going to have to make. Maybe I can make y'all a little note card or something that you can study that says this is what happens when there's a chart in your book. It is on page 128. It's a nice little chart that sums everything up nicely. I will definitely try. I'll try to make you some little colored note cards. All right, if the absolute value of A is greater than 1, it is a horizontal. And the nice thing about this is it does what you think at least it does. So the other one makes sense in words, but graphically it's the opposite of what you think. This one, if I'm my same parent graph, a horizontal stretch is making it wider, right? If you stretched out the horizontal axis, right? It's making that graph get wider. It absolutely is.
Because that's nowhere to go, but.
Right. Remember I told you there was going to be overlap here? Okay. All right, so this would be a horizontal stretch. I really want you, I find it the easiest if you can visualize in your head that's what helps me remember what they are. Horizontal stretch. Take the horizontal axis and stretch it out. If it was in rubber bands and you just stretched it out this way, it's going to make it wider. That's why it's opposite. But if I do horizontal shrink, so now take your hands and shrink that axis back in, it's making the graph skinnier. Huh? So, of course, we're not going to just do one transformation.
No.
But let me just show you in general what this equation could look like. I should probably call this G of X because I've used F of X. G of X, it's just, so we use different letters to name them. So kind of like I call you Dayton and you kind of have to differentiate between the two. This is G of X, it's a different function than F of X is. It's just different. Yeah, if you did this, I'm still going to email me. I'm good. Rich told me that she had already done. I said, well, he's going to be ahead of the game because we're doing transformations today. So, A. What is A?
Horizontal.
Okay. I'm just going to call this my dilation. And we can determine what it is and how it is. H, notice in my equation I put minus H because remember it was the opposite sign.
So you're going to be moving left, right.
So for this one, yes, this would be right. But what I did was I put minus because if I want to move 5 units right, then I'd let H be 5 here.
So if you had X minus negative H, you'd actually be moving
You'd actually be adding, so yes. That's why the equation's written with the minus in it, so that it accounts for, so that you can just say, shift this right 5, plug 5 in for H. Shift this up 2, plug 2 in for K. Shift this left 3, plug -3 in for H. And the equation will account for it. Yes. H is my horizontal translation, because it's in the parentheses here with.
You K's your Y and your Z.
Not necessarily. But K here is my vertical translation.
We're moving up or down.
Up or down, right. Now, let's put it all together, see if you understand. Oh, we don't? Don't say that. You probably do more than what you think you do.
Which one would you do first? Or would that find out?
There is an order to do, and I'll get to that. There is an order in which you have to do it first.
I think to do it, I just have to put my notes right.
There's a little acronym I'll give you to help you remember. All right. It is important for you to remember that dilation does not alter the figure itself, it only alters the size, okay? So if it had points and peaks and maxes and mins, it's still going to have those. They're just going to be in different places, but it's not impacting the figure itself. It's just impacting the size of the figure. All right, tell me. I'm going to start easy. I said we wouldn't use Y anymore, but your book's still using some Y's. So first off, tell me what the parent graph is here. So what's the equation of the parent graph?
Y equals X.
Y equals X squared. What is happening to the parent graph?
Being dilated times 2.
It's being is it a horizontal or vertical stretch or shrink?
It's a vertical stretch and a horizontal shrink.
Okay, so understand the difference here. This, I would say, if f of x is x squared, okay, then this is 2 times f of x. But I could also describe this as f of, are y'all ready for this? Square root of 2x. Because look. If this is this, okay, and you have to understand this if you're going to describe it both ways. Here the x is only being squared, right? If I wanted to say something times x squared, so remember the horizontal dilations only are multiplied to x. What would you have to put here so that whenever you put this through, it would still end up with 2x squared? Well, that would be a square root of 2. Right. Okay, so this is a dilation of square root of 2. This one's 1 of 2. But they're the same. What is this one, horizontal or vertical? What happens when you multiply? What happens with this? Look at your little, and it'll be handy for y'all to have one of these. I kind of noted out each one. Maybe. It's going to be vertical, definitely. It's going to be vertical because it's bigger than 2. I'm bigger than 1. It's going to be a stretch. So this is a vertical stretch of 2. So does that mean it's getting skinnier?
Yes.
Or it's getting wider?
Getting skinnier.
It's getting skinnier. If I stretch that axis out, it's getting skinnier. Because it's multiplied to the front, it looks like this, 2 times f of x.
Instead of the f. But if it's multiplied only by the x.
Right. If I needed it that way, I could also write it here, which would be a horizontal, what? Shrink. Which is still, a horizontal shrink and a vertical stretch are the same thing, okay? But they have some different factors here, as you can see. A horizontal shrink here of square root of 2 is the same thing as a vertical stretch of 2 on this one. Either one you put is fine, but you don't put them both. You just put one, right? Pick which one you're going to do.
So,
So if the parent graph, now it depends on, I would definitely go with vertical stretch of 2 on this one. And here is why. Oh dear. All right, if I have, I'm going to erase all this for just a second. If I have my parent graph of x squared, right? I'll try to put y'all a little cheat sheet on Classroom because I won't have time before you leave today. All right, my parent graph is x squared, right? Which is 0, 0, 1, 1, negative 1, 1, and I'll just leave it at that. This is saying every y, because y is f of x, every y is doubled, right? 0 times 2, this is 0, 0, this is 1, 1, this is negative 1, 1. X stays the same, but y doubles for this transformation, right? 0 times 2, okay? 1 times 2 is 2. Negative 1 times 2, right? Is that a vertical stretch?
Yes.
Yes.
And what are you multiplying 2 by, the y?
The y, because I can write it as 2 times f of x, which says multiply f of x. Remember, f of x and y are the same thing, okay? Now, if I'd have done by the x's, that's why I said you'll want to do it this way, because if I'd have done square, if I'd have gone through and I'd say, okay, y's are going to stay the same, but every x is going to multiply by square root of 2. I don't want to have to graph that. Ugh. Right? Yes.
You only multiply the y.
For this one, yes.
So,
It could. Same thing as a fraction. I expect y'all to have a lot of questions on this. What? X squared divided by 2. Shh. But y'all need to listen to all the questions because they'll help you. X squared divided by 2 is the same thing as 1/2 x squared. So that's going to be a vertical shrink. It's going to make it wider. Okay? Yeah.
so with the 2 times f of x, is that
Yes, yes, yes.
Okay.
That's exactly. And I think y'all might be getting confused too because you need to understand this and this are 2 different graphs. The second one is manipulating x. The first one is manipulating y, unless you transform or rewrite the equation a little bit, okay? So this one is a vertical dilation, this one a horizontal translation. Even though we could rewrite them, this is the same thing as 4x squared, right? Y'all are looking so lost right now.
Yes. Yes, it is.
It's only the dilation.
The dilations, that's what it always is. It's always the dilations.
I mean, I understand how you're supposed to do it, like stretching and all that hot stuff. Just math.
Just, yeah.
Right. Thinking about it for yourself. Those numbers.
Is that the square?
Lots of letters. Lots of letters. Lots of
2 times f of x is saying just throw a 2 in front of the whole equation. It's still there, it's just on the x. All right, look, here's another one. Look at this one. What type of dilation and why?
yeah, that is
Is only a shrink of what?
Or a shrink of your...
Oh, are you sure?
It's a vertical shrink. No, it's a horizontal.
It's horizontal because it's only being done to x. If it looked like this, it would be vertical. It's a horizontal stretch.
because it's being.
If it's only done to X, remember, this is vertical, this is horizontal.
So if there's like two things in there, that's horizontal.
If it's what? Yes,
Okay.
yes. Does that make sense? Does that mean it's getting wider than the absolute value of X or skinnier than the absolute value of X? Horizontal stretch, it's getting wider. Fatter is such a derogatory
See,
word.
that's what I told
I am a
Just-
tall
I'm
fat
kidding.
Everyone
person.
record.
All right, let me show you. Let's put a few together, see if you got it. And I know this is a loaded lesson. I knew it was going to be a loaded lesson before we started on it. So y'all's looks of exactly what I expected. All right, but hopefully when we put it all together, you'll be okay. Tell me this. If my parent graph is this, it's a parabola. Describe the transformations that are happening to my parent graph to get from F to G. I've got lots of stuff happening here. Okay.
It's a reflection.
It's a reflection over which one? X-axis. Which means my parabola is not going up anymore. It's going down, right?
Reflection over the X, and it's moving left.
Translation up, how many? No, not up.
Oh wait.
Side to side. To X is horizontal, so which way is it moving?
Left.
Left 4. Graph that.
Not really like exact.
All right, look. 0, 0, 1, 1, and negative 1, 1. The negative out front. 1 is your average parent. It doesn't dilate it any.
Where does the exponent?
From your parent graph here. Okay. So every point is going over X and it's going left 4 down 1. Okay?
Wait,
Yes.
the negative again?
What?
The negative?
That's my reflection.
Oh, I just got it. That was great.
I
Yes.
think
All right. Over X keeps it here. And then down 1, left 1, 2, 3, 4. Reflect over X and then down 1, left 1, 2, 3, 4. Reflect. Down 1, left 1, 2, 3, 4.
It's not like. I get it. I got it. Because you reflect over X.
I find it easier when you put them all together and see it happening all at once.
Once you add numbers.
I got it.
Okay, I think I got it.
Yeah, you said that numbers.
I just might have figured out the.
Well, I understand how she got it.
Yeah, I understand now.
One more thing to show you. Let's see. I'm sorry.
No, you just gotta flip through the X.
Yeah, I just don't really make graphs. There's not a lot of necessary.
If the parent graph is y equals x squared, write the equation of the graph in green. The parent graph is y equals x squared. Write the equation of the graph in green, and there's no dilations here. What are your shifts, shrinks, stretches, and reflections? Huh? Yeah. Take a second to look at it, and I'm going to pause the... All right, if you got it, you can look up. If not, keep on trying to figure it out. But let's look at it together. Tell me what's happened from the parent to the green. It moved over which way? It moved right 2 and up 1. Right? All right. So right deals with x. If it moves right, do I need to add or subtract? Subtract. And it's in the parentheses because that's what hooks it to x only. Up 1.
I just put an F in front of the I got it. Other than that, I'm good.
Okay? All right. Let me tell you what I want you to do.